Good afternoon, everyone. Thing is, we have only a couple of more lectures to go. So I thought I'll kind of compress the portion a little bit. And so today's class, I'll cover brain and language. Next class, I'll cover brain consciousness. Okay. So let us begin the story of brain and language with this phenomenon of phrenology. I think we have discussed this once in our early classes where we talked about this big history of neuroscience. Right? There was a big debate about the aggregate field view and localization view for a long time. So phrenology is in itself kind of a pseudoscience, but our understanding of the brain function and distribution of functions in the brain kind of started with this kind of a pseudoscience, fortunately or unfortunately. So according to this science, which was proposed by this guy called Franz Gall, who was an Austrian physician. So logic here is that brain is an organ of mind. It has multiple functionalities or faculties, and for each faculty or a function, there is a part of the brain which is responsible for that. And if that quality is strong in a given person, the corresponding brain will be bigger in area or volume. And this part of the brain which is bigger in a given person, relatively speaking, tends to push upwards or outwards into the skull from inside. And because of that, skull takes on a sort of a peculiar shape, which reflects the internal variations of the volume, right, brain volumes. And therefore, as a consequence, you can simply by feeling or looking at the head surface of a given person, you can find out the person's character. So this is the kind of arguments, and it is kind of like palmistry and all these things, right? Which is a pseudoscience. It's simply not true. But it was quite popular because people something interesting, something that seems magical, right? Irrational, of course. Will have a lot of attraction in the common public. So it was very popular for a long time. So there were some objections to this because it's a totally irrational kind of an approach to the problem. So Napoleon, Bonaparte was the king at that time. He asked one of his court physicians or court scientists called Pierre Florence to take up this issue and kind of study exactly what's going on in the brain. So he has taken experimental animals and created lesions in the brain and then looked at their behavior. And then what he found is that mental functions are not localized. All regions in the brain participate in all mental functions. So that was his conclusion, and partly that conclusion, he arrived at that conclusion because he made lesions which are very big. So there was not enough specificity and they were not very sensitive surgeries. So that's his conclusion. It's partly true for a different reason, but it's also, he came to the conclusion because of the bad experiment performed. So there was a lot of criticism against phrenology from many points of view. So first of all, philosophical, because before phrenology, mind was studied by introspection. People just looked at themselves, looked at their thoughts and feelings, and came up with explanations as to why they're getting those thoughts or feelings. Right, but so that was not okay because science is all about objective principles and things that you can measure objectively and so on. Okay, so therefore there's the opposition to phrenology because the people thought that people who liked all this philosophical stuff, right, said you're promoting atheism and materialism because you cannot say everything based on mind and based on the brain, and soul is something immaterial. So you're trying to reduce something immaterial to something material. So that was a kind of philosophical objection to that, which is itself quite absurd. But that was one of the objections. The other more concrete social objection is more like a commercial objection. That is, people who are practicing phrenology are just making a lot of money. That just like astrologers make a lot of money these days. So because of this, there were some objections, and then people wanted for challenging it. We want to test it more rigorously, right? Franz Gall also took the criticism. He responded to the criticism. He said, "Okay, fine, but one thing I can tell you, which is true, which is that organs that control speech and language are in the frontal lobe." Which is a very gross statement because frontal lobe is a huge area and controlling speech and language is itself a very huge function. So to say that these functions are come from frontal lobe is a vague statement, right? That itself is sufficiently of scientific interest in those days. So then Paul Broca, who was a neurologist, right, who was a hardcore scientist, he said, okay, fine, let me test this. So he began looking at certain patients. One of his patients was a chap called Tan. He's a 50-year-old male, and he had speech impairment for 21 years. He could utter only a single word, Tan. Okay, so he could gesture, he could even hum, tunes of songs and things like that. But and also from his gestures, you could see that he can understand what others are saying. But otherwise, he could not utter sentences. His speech was seriously impaired. After his death, his postmortem studies have revealed that his damage is in the left frontal lobe. So something more specific than what Franz Gall has said. There's another guy called, he's just simply called Lilo, because he keeps saying that only, so he keeps saying he could say only 5 words. That is yes, no, 3, always, right, and one more word. I don't know what it is, right, and he was called Lilo because it's actually a distortion of his name, Lilong. And in this case, too, postmortem studies revealed that there's damage to the left frontal lobe. So based on these kinds of studies, Broca proposed that there is a specific kind of speech disorder, right, an aphasia, which means speech disorder. It's named after Broca, therefore it's called Broca's aphasia. So in patients with this kind of aphasia, can understand language, but they cannot speak. And they don't have any conventional motor deficits of the tongue, because if you say wag your tongue, they can wag their tongue, right? They can produce sounds, right? Simple non-speech sounds. They can utter isolated words or even sing a melody. So which means, right? But they cannot express grammatically correct full sentences. The other people can, these are extreme cases. There are people who can express some single words, but not grammatically complete meaningful sentences. And in most cases, the lesion was on the left side of the brain and in the frontal lobe. So this prompted Broca to declare in 1864 that whatever the French sentence, nous parlons avec l'hémisphère gauche. Okay, so we speak with the left hemisphere. So the so-called Broca's area is located somewhere here. It's shown by the red disc or red oval shaped thing in this slide, and it's on the left side. So similarly, there's another guy called Wernicke, Carl Wernicke, who studied a patient with a different kind of aphasia. In case of Broca's patients, they could understand but they cannot speak, whereas Wernicke's patient could speak but could not understand. So it's opposite problem. So it's a receptive problem as opposed to expressive problem. So in this case, the lesion was located in the posterior part of the brain, so which is roughly shown there in the red region. So they can utter sentences, but doesn't make much sense, right? They cannot understand, right? As this is a language. So, for example, an utterance from a Wernicke's aphasia patient might look something like this: I called my mother on the television and did not understand the door. It was to breakfast, but they came from far and near. My mother is not too old for me to be young. So it doesn't make any sense. It's the language the sentences are framed correctly, they're grammatically correct, but they are they have no sense, right? This is a typical kind of a problem with Wernicke's aphasia. Then there is a third kind of aphasia, which is called conduction aphasia. So in case of Broca's, it's a problem with speech expression. In case of Wernicke's, it is problem with first one is language expression. Second one is language comprehension. In this third kind of aphasia, the problem is the patient can understand words, right, and whatever they've read or whatever they've heard, but they cannot repeat phrases. Okay, and in these patients, the problem is anatomical problem is in a bundle of fibers which connect the Broca's area and Wernicke's area, which is called arcuate fasciculus. So obviously, to repeat something, you have to, and especially if the phrase is sufficiently complex, right? You have to capture that phrase, understand it, and then repeat it, right? So which means information. So you can understand the phrase only in your Wernicke's area, and you can utter the phrase in your Broca's area. If you have to repeat what you have understood, then you have to have some way of transferring or transmitting the information from the Wernicke's area to the Broca's area. That is done by this cable. This is called arcuate fasciculus. So these people can speak fluently, but of course they're not language is not very correct. There are a lot of mistakes omitted parts of sounds or substitute incorrect sounds. For example, in this case, in the previous case, you can see, you can guess that breakfast actually is substitution of fast. So it was too fast has more better meaning, has some meaning. Because too breakfast has no meaning. All right. So they do this kinds of substitutions. They're aware of their problems because they can understand what they're saying, but they're not able to correct them, especially when it comes to repeating what they've heard. So in this case, the problem is with this bundle of fibers. So you see that right there, you see an outline of language architecture or the architecture of the language system in the brain, language processing system in the brain. So there are three areas or two areas connected by by bundle of fibers. There's a language comprehension area, which is the Wernicke's area, language expression area, Broca's area, and a bundle of fibers that connect the two, so that you can express what you have understood. So based on this, Wernicke made a summary about brain function in general. He's not just talking about language function. So because there's a big debate for for centuries whether the brain functions are localized or distributed. He said simple functions are localized, whereas the more broader functions are distributed and is conducted by many areas in the brain working in parallel and spatially distributed. So he calls this kind of a operation of the brain parallel and distributed processing. And it stuck, this expression stuck even in the 80s when the connections revolution has taken place. Right? People have used this expression as it is, parallel and distributed processing, as like a buzzword to understand, to explain how brain works. But in spite of that kind of a clarity which came long ago, like late 19th century, people still have tendency to say that, oh, this part of the brain does this. Okay, it doesn't work that way. It's always a big network, right, performing some function. But still, we like to think that this neuron responds to something. This neuron does something. This part of the brain does something. So it's a kind of habitual to talk like that because it seems to make life easy. So now Broca's and Wernicke's area obviously are not the whole story. So we need to ask the question: what comes before them? What comes after them? So let us try to make sense out of that. So we have looked at this kind of simplistic brain models, even some of the earlier classes. Think of the brain as a big black box, so like an input-output function, right, which takes input, sensory input, and then produces motor output. And think of it as a big deep network with lots of layers in between. So sensory input that comes in goes through a bunch of layers and goes to the motor layer, right, and then produces motor output. And so you can put more layers, as many layers as you want between the input and output layers. The input layer itself can be divided into multiple streams, where each stream corresponds to a certain sensory channel, like sound and vision and touch and things like that. Similarly, motor output also has multiple streams. You have movement of the eyes, movements of the hands and legs, and speech and so on. Okay, so now let's look at to consider language. Language. Let us look at what are the input channels and what are the output channels. Okay, so for example, language can be understood by reading printed text, right, or listening to speech. So let us consider those two channels. There are more. I mean, you can even understand language by touch, for example. But let us look at these two. Let's say you're reading something, and so your input is coming from visual channel. So that goes to certain neurons or certain part of the brain which process vision, right? And we know the visual system and architecture, or we have some idea, right? So similarly, let us say we are listening to some speech sound. Somebody is talking to us, and we're listening to that. So that comes to the speech channels, right? It comes to the ear, the cochlea, and then climbs up the various inferior nucleus and right, inferior colliculus, and then you have medial geniculate nucleus and all those things. Then finally it comes to the primary auditory cortex, and then it goes to the higher association areas. Okay, so similarly for touch also, if you're looking at somatosensory area, let's suppose somebody is reading text through braille, right? The text input is coming through touch information. Okay, and that also goes somewhere. But once it goes to certain point, certain sufficiently high stage in the brain, you would imagine that all of them come together, right? Whether I read a word apple or whether I listen to the word apple, somewhere in the back of the mind, I have this representation of the word called apple, right? So obviously, whatever be the source, all these sources lead to the same representation of the word apple. So you would imagine that there is some point in the brain where this word representations are created, irrespective of their sensory origins. Right? Whether the word has come from the visual source or an auditory source, it is the word apple, APPLE, right? Or whether it's come through some kind of a tactile input, it's all come to the same word. So thing is, so there are areas in the brain in the postparietal where in which broadly call sensory association areas, which combine inputs from multiple sensory sources. So especially these are the areas which combine information from vision, sound, and touch, right? So and several of these areas are right next to the Wernicke's area. So it makes sense. It's quite logical. The sensory association areas are right next to the Wernicke's area, right? So if you so I think there's a color coding of various areas here. So visual cortex is red, and this pure white is auditory cortex. Now, auditory association is given the whole gray area is auditory association, but actually it's not that big. Auditory association is also still confined to the superior temporal gyrus, this upper part of it. Now you see this, I don't know what color it is. I'm not very good at colors. Kind of yellowish green or whatever, right? So that is Wernicke's area. So you see that this purple area is visual association area, right? And so kind of this person has taken liberties with naming of regions. But anyway, the point of the essence of the whole thing is vision is here, sound is here, and touch is here. Right? Association areas are somewhere in between. And Wernicke's areas are even in the middle of these different kinds of sensory association areas. Right? So which makes sense because obviously the language is independent of the sensory origins. The linguistic representations of word are something that you create by by taking information from these sensory sources, but ultimately you have to create something that's independent or that transcends the sensory origins. So it makes sense that it is somewhere right in the middle of all the sensory association area. So that is your Wernicke's area. Now let us see what happens on the motor side. So on the motor side, you see this orange area in the frontal lobe, that is your Broca's area. And note also that the Broca's area is right next to the primary motor cortex, which is shown in this, I don't know what color it is. It is in the precentral gyrus. So you see that, so this is like the motor homunculus, right? Which that it looks like inverted human being. So the tongue and lips and face representations are all in the lower part, whereas legs and trunk and all that is in the higher part. And feet is almost in the medial portion. So it kind of, you have to dive down between the two hemispheres. So why is the Broca's area right next to the lips and tongue and face? And it makes sense, right? Because Broca's area is all about controlling lips and tongue and face and jaws to produce speech sounds. Okay, so the Broca's area is slightly at a slightly abstract level. From there, commands go to these lower layers, which actually send commands to the muscles of these various body parts. So it makes sense that Broca's area is right next to these parts of the primary motor cortex. So one thing that you see in this is there's a very logical organization of these different brain areas. One is that brain areas performing similar functions are close to each other. And why is that? Because there is this all important need to minimize wire length. Therefore, it makes sense to put function areas which perform similar functions close to each other in the brain. But the thing is, Wernicke's area is not a singular distinct area. It's just as sensory association areas is not a single area, because you can have association between touch and vision, and there are such areas. You can have association between sound and vision. There are such areas. So similarly, sound and touch. So there are several sensory association areas. Similarly, there are this idea of the classical picture of Wernicke's area as one compact region all in one place. That's not quite true, because modern imaging studies have shown that it's slightly distributed even there. But anyway, we are not that interested, because just by calling a region Wernicke's area and saying that language is comprehended here is absurd, because things don't work that way. Now we understand that quite well. Okay, so there is some kind of a vagueness in identifying this, but that's okay, because we're not into that. It's not an important question in the first place. So similarly, the idea of Broca's area also needs some revision, because so many people who are who have Broca's aphasia have trouble understanding syntactical structure of complex sentences. So thing is, the classical definition of Broca's aphasia is that they have trouble speaking, but they can understand. Yes, but problem is to speak well, you need to be able to understand. Without understanding, your speech output also will be affected ultimately. So therefore, more recent studies have found that Broca's aphasics also have problem with understanding longer sentences, more complex sentences, right? Because the whole thing is a loop. You cannot separate the input and output and say, okay, this guy can process input but cannot produce output, or can produce output but cannot process input. That doesn't make sense, because input and output form a loop. Because you understand, you are able to produce language or speak effectively because you listen to what you are saying, right? And then correct yourself on the fly as you speak, because when you think you have uttered something wrong, you go back and correct it, right? And that's why if we are talking some nonsense, let's say you're talking some nonsense to a friend, they'll ask you, hey, are you even listening to yourself, right? Do you even understand what you're saying? That's because understanding what you're saying is necessary to be able to produce meaningful speech. Now, stroke patients with damage to Broca's area are also able to recover speech after some time. So this is another kind of a counter example to the classical simplistic picture of Broca's area, which is that, okay, in some stroke patient, Broca's area is damaged. So temporarily there's loss of speech, but after some time they recover, right, and recover speech. So in these cases, typically what happens is nearby areas in the brain take over the function of the lesioned area, and then after that, in future, that new area becomes a Broca's area. So again, these things are not cast in stone. Things are a lot more flexible and dynamic in the brain. Secondly, and even the Broca's and Wernicke's area are actually quite close. So in fact, they are called the perisylvian areas, right? Because if you look at this picture, so you have the frontal lobe here and the temporal lobe, and then there is a border separating these two. That's called the Sylvian fissure. We have seen it before, right? You can kind of put a scapula and dig deep, and you will see a deep fissure there. And this fissure acts like a border between frontal lobe and temporal lobe, partly, and also if you go deeper, it will act as a border between parietal lobe and the temporal lobe. Now, the Wernicke's area is on the inferior side, like below the Sylvian fissure on one side, and Broca's area is is above the Sylvian fissure on the other side in the frontal lobe. So you call them the perisylvian. So they are on the. It's like if you think of the Sylvian fissure as a river. These two areas are on the two banks of this river, right? Therefore, they are called perisylvian. And why is it like that? Like I was just saying, these two areas don't operate in isolation. They're closely coupled and they talk to each other all the time. That's why even for them to perform their individual functions, they have to closely communicate with the other region, because the language comprehension, language production acts as a loop. Okay, so let us try to understand this concept, which is very important. Let's take a closer look at this. So imagine that, let's take a very simplistic kind of a schematic where, this is a Broca's area of some person and there's a Wernicke's area. And there are kind of neurons, let us say, which present certain basic sounds, right? And then on the Broca's area, which means if the neuron is activated, the sound is produced by the person's speech apparatus. Similarly, on the Wernicke's side, there are neurons or neuron clusters which are responsible for understanding or processing for certain speech sounds. That means if they hear that sound, these neurons will respond. Now imagine that initially so you have the two sounds we are considering is ma and pa. These are very basic sounds. Even babies utter these sounds. In fact, that is the reason why we name parents as ma and pa. But these are some of the sounds that babies commonly utter naturally. So it makes sense to name yourself after, right, what babies can call out. So so the ma neuron in Broca's area and this pa neuron in Broca's area, right? So now imagine that initially, for whatever reason, the connection between Broca's area and Wernicke's area are random, because it's still a young brain and connections are not well formed. Let's say the two are randomly connected. So it so happens that the ma neuron in the Wernicke's area is connected to the pa neuron in the Broca's area, and Similarly, PA neuron in the Wernicke area is connected to the MA neuron in the Broca's area. Now, what will happen is, so the MA neuron is activated. So the person or the baby produces sound MA. That is heard by the Wernicke's area because the ears are open, it has heard Wernicke's area. So then the MA neuron gets activated. So the MA neuron in the Broca's area gets activated. That causes the MA neuron in the Wernicke's area get activated. So these two neurons get activated repeatedly together, because of course with a small delay. Now the two neurons are connected by a fiber. The only thing is this connection strength, let us say, is initially weak, right? And these two connection strengths are initially wrong connections are active or strong, whereas the correct connections are actually weak. But what will happen with this kind of a repeated utterance of these sounds is the MA neurons in the Broca and Wernicke's area kind of get activated together, right? And the PA neurons will get activated together. So what happened, there is a rule that says, there's a kind of a learning rule called Hebbian learning, which was proposed way back in the late 40s by a person called Donald Hebb. So he proposed this very general theory that in brain learning occurs by some kind of adaptation or a modification of neuronal connections. So that was a time when we didn't really know much about synapse or synaptic function, neurotransmission, all that came, especially the idea of LTP and all that, that is adaptation of synapses and all that came later in the experiments done in the 60s. So this guy made a good guess, had a good insight into what might be happening at level of neurons. He said if two neurons are connected, and so depending upon the ongoing activity patterns of the two neurons, the connection strength between two neurons will be either strengthened or weakened. So how does it work? Let us say, consider this cases. Initially, the connection is, let us say, weak or moderate. If it so happens that whenever A fires, B also fires. So because both A and B receive inputs from many other neurons. Okay, so it so happens that whenever A fires, B also fires, let us say. Like in this case, for example, whenever this MA neuron fires in the Broca's area, MA neuron in the Wernicke's area also fires, because that's how they are arranged. Then the connection strength between two neurons will be strengthened further than what it was before. Whereas imagine where the situation where whenever A fires, B doesn't fire or rather fires at a very low output. In that case, the connection strength is weaker, right? Or similarly, vice versa, right? A doesn't fire or fires very little, but B fires very actively. Then also the connection strength is weaker. So the moral of the story is the pattern that you are seeing here is when two neurons are connected, fire together most of the time, the connection strength must be increased. If they don't fire together or fire in out of sync fashion, then the connection strength must be decreased. So it is captured in this very nice formula that says neurons that fire together wire together, and that's exactly what is happening in this. The way the connections are adjusted between Broca's and Wernicke's area. In this example, we can see one more thing, right? It can see how closely coupled two areas are. Therefore, to think of them as isolated areas performing independent functions is absurd because they form a loop. Now, so these kinds of connections form at a very early age because so this kind of mapping between presentations of basic sounds, both in the Broca's area and Wernicke's area, right? They form the basis for generation of much more complex sound patterns, acoustic patterns. So therefore, these basic maps must be laid out at a very early age. And in fact, this seems to be happening even in small infants. So I don't know, if you have little nephews and nieces at home, or if you have had a chance to observe them, they engage in incessant talking like this.
Sir, the audio is not, we are not able
Oh
to
God,
hear.
this again same problem. Okay, what I'll do, I'll send you these slides. You can look at the audio. Basically, this baby is. Can you see the video? I mean,
Yes.
are you able to see the video? Okay, what this fellow is basically doing is he's saying pop, 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 pop. That's all. Right. So that's called babbling. Now, babbling, babies do it spontaneously. Okay, so these are the some of the basic sounds that the vocal apparatus of a baby is capable of producing naturally without any training. So they do that. So when they do this, these basic maps keep forming between the Broca's area and Wernicke's area. Now, babbling is a very important stage, very early stage in the language development. But it happens, begins very soon after the birth, and if at a few months, right into the life of a baby, and progress in stages leading on to speech-like vocalizations. Because babies watch their parents or whoever it is, caretaker, speaking to them. That's why it is generally said, you should talk to the baby. The baby may not understand what you're saying, but baby will be trying to imitate your sounds. In fact, birds also, songbirds, right, like cuckoos and quail and all that, they learn like this. So they learn from the not necessarily mother bird, but there's something called a tutor bird. The senior bird will take the trouble to teach the younger bird how to sing. So the syllables of the senior bird or tutor bird are imitated by the baby bird, right? And that's how it learns to sing. So it is thought to be, babbling is thought to be a precursor to language development, and infants babble mimics the prosody of the language as are exposed to. So the kind of musical quality of a language, and that's different for different languages, right? That side of the language is already captured, or you can see that there is evidence that that side of the language is influencing the babble of infants. And babble consists of vowels and consonants, more frequently found in the mother tongue of the infants. The thing is, there's huge number of vowels and consonants, but the kind of vowels and consonants you see in babble, baby's babble, is strongly dominated by the mother tongue of those infants, because these are the kinds of sounds that the infant is exposed to very early on. Right, so the babbling, like I was just saying, it seems to create some kind of a map between the auditory representation of the basic speech sounds in the Wernicke's area or on the input side, and the corresponding motor representations in the Broca's area. So with all this, we have seen that first of all, there is this, simply put, there are two partitions: language comprehension, which is the Wernicke's area, and language production, Broca's area, and the two are connected by bundle of fibers. And these fibers are adaptive, and so very early on, the maps of basic sounds on the Wernicke side are kind of aligned or calibrated against the maps of the sounds, right, or the motor aspects of it in the speech area, in the Broca's area. Now the Broca's area, when it is activated, it sends commands to the actual motor area or speech motor area. So this is a part of the primary motor cortex which actually controls the muscles of the speech apparatus. So this is how the motor side hierarchy works. There's a descending hierarchy on the motor side where you have slightly abstract commands of speech sounds in the Broca's area, and the actual, which is elaborated into actual muscle activations in the primary motor cortex. So that's how the motor hierarchy works. On the sensory side, where input comes from an auditory and visual and even tactile. So these are processed up to some point, and then after that they become more abstract language representations, and that is what is processed in the Wernicke's area. Okay, so this is a summary of the language architecture in the brain, a language linguistic functional architecture in the brain. Now let us ask this question. So you have two things: language production, language comprehension. Is there anything else? Okay, so let us look at some existing theories. There is something called three-system theory proposed by the Damasio couple, Antonio Damasio and Hannah Damasio. Now both are neuroscientists and a couple. So they propose that there are three systems underlying language processing in the brain. One is the sensory motor system, which is a very low-level system, where the sensory side you are processing the visual input, right, or processing the speech sounds and so on. On the motor side, you are moving your tongue and jaws and larynx and all those things. This is a very low-level aspect of it. Then the higher-level aspect of language is, right, the words and rules and the rules of grammar, syntax, the phonemes and syllables and all these things. These come at a higher level. So these people have proposed that between these two, there is a bridge system that connects the above two systems so that it works out some mapping, right? Because you can imagine that the mapping can be quite complex. It's not a one-to-one mapping or anything. So there is a concept system which comes out of the sensory motor experience in the world. Then there is a language system which has all these representations for phonemes and syllables and words and syntax and all that. And there's a third system which works out the connectivity between these two. Let's take an couple of examples. An example of the word running. Running has sensory motor connotation because when you actually run, right, your muscles of your body are activated in some pattern. So it's a huge pattern of activation of the muscle. It's not a simple local thing, right? And then even your autonomic system is activated. You have increased perspiration, increased heart rate, and all those things. The sympathetic system is activated. Then on the visual side, right, you will be looking at the world coming towards you, and actually you are expanding in front of you, right? We'll see this optic flow of the world in front of you. So you'll see it expanding from some kind of a vantage and a vanishing point. So all this is the sensory motor aspects of running. So on the language, in the language part, the word running can be used in speech. Like I like to run. I am right now running. Don't disturb me. I didn't go for my run in the morning today. Whatever it is. So then you can express it in speech and handwriting, and you can type it out as an email or whatever. Now, so they also give the example of they give the example of the system in case of color perception. Now, colors are processed obviously by starting with the visual input coming from the eyes, which is processed by various visual cortical areas. And finally, there is one part of the visual system, visual cortical network. It's called V4, where colors are processed. This is the highest center in the brain which processes colors, which is representations for colors. And mind you, this is not the words corresponding to color. This is a concept of color, because you can you not know the name of a color, but you can answer the question: is this color, is other color, right? You may not know what color is named, right? But these two colors are the same. So that is a color concept. So so this V4 is involved in that kind of a color concept, and damage to V4 will create a problem of inability to perceive color, which is called achromatopsia. So you might have heard of something called color blindness, which occurs because of damage to the retina. That is, in retina you have three kinds of cones, right, which are responsible for perceiving, for processing three different wavelengths, roughly correspond to R, G, and B. But the V4 damage causes is a whole different story. Color blindness refers to the damage to the cones, or more specifically, some of the dysfunction of the proteins that convert that light wavelength into reticle signals. Whereas V4 damage is different, right? It's a very high level thing, because concepts are processed here. Damage here creates a sense of inability to perceive colors. Now there's a damage to a different system called a language system, and if this lesion is close to Wernicke's area, and there is a region where subjects have trouble naming colors. The V4 is for color concepts. This other region which these people have identified close to the Wernicke's area is into it maps color names, right? And therefore, people with damage to this particular area, which is responsible for color names, they can process colors. They can do color matching. They can classify them, right? They can say that all these colors are similar to each other. They form a cluster, right? And so on. But they have trouble with naming colors. So, for example, color names. For example, when if you show them the yellow color and say, what color name is it? Instead of yellow, they might say hello. Okay, so they caught the word wrong, right? And and then that is the thing. Then there's a third system they are saying, which is damage to the bridge system, which is if there's a lesion close to the temporal part of lingual gyrus. Sorry, the figure is somewhat weak. See this orange area here, right? So that's the lingual gyrus. So if there is a damage there, right, the patients have trouble matching the color names to the color concepts. So color names is represented in one area, color concepts in B4, right, and then the bridge system is the one which connects the two. So if there's damage specifically to the bridge system, then these people might be able to match the color of a cricket ball to the color of a tomato. But when they're asked to name the color, they might respond. So that means they know the color concept, right? When you ask them to name the color, they might say it's green or blue. For some other thing, if you ask them to name the color of lemon, they might say red. That's a different thing. So point is they know the color names. It's not that that part is damaged. They know color concepts, but the mapping between color names and color concepts is messed up. So therefore they do wrong kind of mapping. So this is the kind of concept, kind of theory of language representation that these people have proposed, based on some clinical studies, based on some patient studies. But this theory also has some problem because words seem to be localized to language studies, yes, but the concepts, right? Because these people have identified a very tiny region for color concepts, which is V4. That might be true for color concepts, but in general, word concepts are not localized like that. They're all over the place in the brain. They seem to be really widespread. So what does it mean to connect, words to color to word concepts? Right. So where does the brain represent the meaning of a word? Let us look at that. So a lot of progress in answering this question has come because of developments of functional imaging techniques like this, right? And so with functional imaging, like PET scan and fMRI, you can say that. So depending upon the activity that the person is engaged in, specific parts of the brain brain respond to that. So for example, when you are listening to sounds, right? You see that in the first top left figure, you can see the auditory area is activated and Wernicke's area is activated. When you are seeing words, visual area is activated. This is near the occipital pole. The Wernicke's area, you can also notice here that the Wernicke's area, or the second area which is activated, slightly deeper inside the posterior brain, right, is not exactly the same as the Wernicke's area that's activated when you are hearing the sounds, or hearing the words. So that shows that Wernicke's area is not one singular, compact region. It's that itself is a cluster of regions. Similarly, when you are speaking sounds, right, your activation is seen in the Broca's area and also part of the primary motor cortex. And similarly, when you are generating sounds mentally, silently, without speaking them aloud, then you see your Broca's area is particularly activated. So these kinds of studies have been done. This is one of the earliest studies. You can do a lot more interesting things with fMRI, which is more dynamic, which has a much higher temporal resolution than a PET scan. So people are able to find that when it comes to word representations in the brain, or word concept representations, there are these sensory and motor words, and there's a very gross kind of classification. So here the idea is you select words with a strong sensory versus motor connotation. And what does it mean? All right, and if you present them, will only the corresponding brain areas respond to them. So for example, sensory words like giraffe and koala bear. Why do you call them sensory words? Because you only get to see them. You won't act on them. You don't play with a giraffe, or you don't push a giraffe or things like that, right? It's only mostly purely sensory. Even koala bear. How many times have you played with a koala bear? Because I've never even seen one. So they call such words sensory words. And motor words are those where they are associated with some kind of an action, with a hammer or a wrench, right? You tend to do something with it. So it has a very strong motor connotation. Then there are mixed words like cat and dog. Here they are mixed, right? Because you see them all the time. You can also interact with them. So there is some kind of a motor aspect to it. So they have somehow taken these three kinds of words and presented them and have observed in imaging studies which parts of the brain respond to these different kinds of words. So they have shown these pictures of these correspond to these words to subjects and asked them to name them silently. So when they were shown a picture of a hammer and when they named it silently, right, in the mind they called it hammer. The premotor area and the middle temporal gyrus, which is the visual motion area. So there's a part of the brain which responds when you see moving images. right? It's called MT and MST. So hammer is always about action, right? So therefore, whenever you are working with a hammer, it involves some kind of visual motion and also some kind of motor activity. So therefore, even when you look at the picture of a hammer, the brain's motor areas and the visual motion areas are activated, which is quite interesting. So that's how brain responds to that whole concept. Then in task 2, when subjects were asked to name the animals, giraffe and koala bear and all that, silently, the occipital area, which has a lot of visual areas, is activated, and inferior temporal area, where complex objects are visual objects are represented. So we have seen that in one of the last classes, right? So this activated for the purely sensory areas, sensory words. Similarly, for nouns and verbs, right? Verbs have a strong activation near the motor cortex, right? And nouns, especially if nouns have a strong visual content, they have activation near visual cortex. And verbs versus nouns, if you compare them, right? If you take them, so take certain verbs and nouns, both of which are associated with action, right? So then again, they see a similar activation pattern. So what matters for the brain is not whether it's a verb or a noun. What matters is the verb or noun is associated with purely sensory processing or motor processing. Okay, so which is so to summarize that, distribution of words on cortical surface is not on grammatical lines, right? Not on lines of syntax and semantics like verbs and nouns and all that, but in terms of word meaning or semantics. So similarly, the other experiment which showed very specific kinds of lexical impairment. So for example, hey, just 1 second, somebody is knocking on the door here. Hello. Yeah, sorry about that. So so here is a patient or a class of patients whose brain was affected by herpes simplex virus or encephalitis virus. So it's not indicated exactly where the damage is, but in these patients, they were able to identify inanimate objects, but not animate objects and foods, which you would think is a very strange kind of a deficit, right? They can only name some objects, but not some other objects. Okay, but this is seen in a real patient. Similarly, another patient who has a massive infarction or damage in the left hemisphere, which is also very generic, non-specific. They could identify animals, foods, and flowers, but not certain categories of inanimate objects. So you see these kinds of things. Now, again, when the action verbs were presented to the subjects, like running, waving, talking, so within the action verbs, again, brain responded differently to different types of action verbs. Right. So, for example, when they were presented verbs like running, waving, and talking, the corresponding parts of the motor cortex are activated. So when they heard the word talking, right, the parts of the motor cortex which are involved in talking are actually they're not actually talking. They heard the word talking or they read the word talking, and in response to that, these parts of the brain are already activated. So similarly, when they heard the word running or when they read the word running, the parts of the motor cortex which are involved in running, like legs and foot and toes and all that, they got activated. Now, people have done a lot more kind of extensive studies of how brains respond to words. So this group called, headed by John Gallant in UC Berkeley, right? They have presented a huge number of words and then looked at the brain's response in fMRI, right, scanner. And so classified, I don't have details, but so they categories. They have shown like which category of words produce a response in which part of the brain, and it's extensively distributed. And so basically what this shows is the kind of picture we started with, that is Wernicke's area for language understanding, Broca's for language production, all that. It's only a small part of the story. So when it comes to actual very low level representations, right? Wernicke's area and Broca's area, they're still there, and they form the kind of the skeleton, right, of this entire language function or language network in the brain. But for the word meaning or word concept or semantics, right, it's pretty much the entire brain is involved in this in responding to that. Okay, so there is a skeletal system which is involved in producing language and compressing language inputs, but that is just for the word production, word understanding. But when it comes to word meaning, it's pretty much all over, everywhere in the brain. Okay, so we can put them in the bigger context of the whole brain, right? Visual hierarchies and sensory hierarchies on the feeding into the Wernicke's area, and motor hierarchies descending down from the Broca's area, and these two connected, right, by arcuate fasciculus by direct connection at a higher level, through prefrontal cortex. This is, so we are basically trying to put the language architecture of the brain in the bigger context of the whole brain. Okay, so with that, let us stop. So because I don't want to do a full language thing, because that will take one more class, and we are short of classes. So what I will do in the next class, I'll cover about consciousness and brain, and that will be the last class, and we can wind up.